Hi everyone, Mrs. V here, and today we are going to look at a very interesting group of compounds. In fact, your body is making these right now as we speak. Today we're going to meet the carboxylic acids. So the carboxylic acids contain the group C double bond to O and then OH. But what do dogs have to do with carboxylic acids? Did I just get tired of looking up chemistry and started searching up cute dog pics? No, not at all. We are going to find out. So, as far as carboxylic acids go, the first thing you are going to notice when you meet a carboxylic acid is that it stinks. Absolutely disgusting. Carboxylic acids have some of the nastiest smells of any of the organic compounds. The small ones like methanoic acid and ethanoic acid just smell a bit sharp. You're familiar with ethanoic acid, that's vinegar. The first 5 members are said to smell goaty. I'm not quite sure if I have any mental picture of what goaty is because I don't smell a lot of goats. I know butanoic acid is one of the most foul smelling substances ever. That's the acid that smells like vomit. It's in rancid butter, body odor, foot odor. So you'll know if you are near a carboxylic acid. Your nose will tell you. So let's have a look at the carboxylic acid group itself. So we have a carbonyl group here and a hydroxyl group, so hence carboxyl. And of course, the presence of this hydroxyl group is going to allow carboxylic acids to hydrogen bond to each other. In fact, this hydrogen bonding is even stronger than the hydrogen bonding between alcohol molecules, and therefore the melting points and boiling points are much higher. These guys have really high melting points and boiling points. They're probably the highest melting points and boiling points that you get in organic compounds. And remember, you can only compare molecules of similar molecular mass because that keeps the dispersion forces equal. Now, in a pure carboxylic acid, you actually get hydrogen bonding occurring between 2 molecules. So this is called a dimer. So you've learned about polymers where you have many molecules joined together. This is a dimer, so it has 2 molecules joined together. And that hydrogen bond means that you actually have the pure carboxylic acid existing in these pairs, which actually makes the size of the molecule double. And of course, that means the dispersion forces are larger, and that leads to a higher melting and boiling point. Of course, as far as solubility goes, we know that if there's a hydroxyl group present, then you can have hydrogen bonding with water. And so we see, very much like the alcohols, the smaller carboxylic acids are water soluble. In actual fact, they're actually partially ionized. They are acids after all. But as the length of the carbon chain increases, we see greater dispersion forces and less solubility. Just want to pick up on the word hydrophobic here. When things are non-polar and they don't dissolve in water, we say they are hydrophobic. So that's water hating. So they don't dissolve in water. These will, of course, dissolve in non-polar solvents like hexane. Now, as far as chemical properties go, these are acids. So they have all of the normal properties of acids. And of course, they partially ionize. You remember from our study of acids that this hydroxyl group is polar. And in fact, we actually have a big drawing of electrons towards this carbonyl group. So this group here is really good at sucking electrons away. So this is really, quite a large delta plus on this. And that, of course, means that that hydrogen can be donated. So we see that this comes off as H plus. So this is going to produce what we call a carboxylate ion. So this is a carboxylate ion. And of course, if we put this into water, then we're going to also get the hydronium ion. So if we added water, we're going to get the hydronium ion over here, just in a typical acid-base reaction. All right, I want you to pause the video and I want you to have a go for, here we have 1, 2, 3, 4. So that is butanoic acid. This is the vomit acid. And I want you to write an equation for its ionization in water. We'll be back with the answer. Okay, so remember, this is the acidic hydrogen here. It's going to come off. So if we add water, then I should have made this an equilibrium, of course, because they are weak acids. Can't lose our equilibrium skills just because we are dealing with organics. So this is an equilibrium reaction. So we have H1, 2, 3, 4, O minus. There's a reason why we have skeletal formulae. Hydrogens are really difficult. Okay, and of course, then we form a hydronium ion. As far as the ionization equation and naming the carboxylate salt, let's have a look. Here is our 1, 2, 3, 4 from butanoic acid. This would be the butanoate ion. So what would the next one be called? That's right, we have 1, 2 carbons, so this would be the ethanoate ion. If you have attached groups, you simply just add O8 ion instead of oic acid to what the acid would have been called. So this is 1, 2, 3, 4, 5, 6. So this would have been 2-methyl hexanoic acid. So this is simply the 2-methyl hexanoate ion. Now, because they are weak acids, they undergo all of your typical acid-base reactions. So they'll react with metal hydroxides. So you remember it's acid plus metal hydroxide. Gives metal salt plus water. They'll also undergo reactions with metal hydrogen carbonates and metal carbonates to make a metal salt. And water and carbon dioxide. They'll react with metals to release hydrogen gas. So it's exactly like you'd expect for any acid. So let's have a bit of a go here. Let's write out what the structure of the organic product is. When we're doing organic chemistry and we're looking at reactions, we're generally only interested in the organic product. So that means we don't have to worry about the water and the carbon dioxide and or the hydrogen. We just draw the structure of the organic product. So often instead of this, you'll actually see the arrow written with just the reagent written on the arrow. So what will we form here? This is our acidic hydrogen here. So we're going to form this ion, and this will be combined with a K+. Remember, when we write ions, organic ions, we write the organic part first, and then we just tack the metal ion onto it. It wouldn't really matter, though, if you left that bit out, because we really are only interested in that organic part. All right, try this one. What will we get with zinc? So I'm just going to draw my arrow with zinc. So we're looking at, instead of that, we're looking at acid plus metal, of course, gives salt plus hydrogen gas. Let's have a look at what the structure of the organic product is. We have 1, 2, 3, 4. Our carboxylate salt, and we had a methyl group here and a methyl group here. You could go and name that if you wanted to. Let's do it. We love it. We love a bit of nomenclature. So this is 1, 2, 3, 4, 5. So it's a pentanoate, and it's a dimethyl pentanoate. So this is 3, 4 dimethyl pentanoate ion. So the actual product would be zinc 3,4-dimethyl pentanoate. All right, your turn. I want you to pause the video and draw the structure of the organic product. We'll be back with the answer in a minute. Okay, so again, I'm going to just draw my arrow here. Magnesium carbonate. So our metal salt, we're going to draw our benzene ring here. Then there it is. That's our organic product. All right, here's a tricky one. What do you do? What would happen if there were 2 carboxylic acid groups? Well, of course, both of them would ionize. So if we add zinc hydroxide here, then both of them are going to form a salt. So this one will form a salt, and the other one will form a salt as well. So this would work very nicely with zinc, because we'd end up with a 1-to-1 ratio of the zinc ion, which is 2+, and this ion, which I am not even going to attempt to name. But that is just showing you that these carboxylic acids react just like any acid would react. Now, the interesting thing about carboxylate salts is that they're ionic, and that means they're very water soluble. And this is because instead of forming just hydrogen bonds between water molecules and the organic substance, as we see in the acid, so if we're looking at the acid, we have hydrogen bonding, but when we have the carboxylate salt, we can get ion dipole bonding. And you might remember that ion dipole bonding is the strongest of the secondary forces. So you will always find, so ion dipole, the negative ion would be attracted to the positive hydrogens. So this ion dipole bonding makes the carboxylate salt much more soluble than its corresponding carboxylic acid. This is very useful if you're actually trying to remove a carboxylic acid by extraction. You can actually turn it into a salt and dissolve it in water. This is also this property is made use of in medicinal compounds. A drug like aspirin and other painkillers, they contain the carboxylic acid group. And so that you actually get them to be water soluble, because nothing is going to be able to pass into your blood unless it's water soluble, you mix the drug with sodium hydrogen carbonate or sodium bicarbonate, which is a harmless substance in the body. And then when that tablet dissolves in water, then you get that reaction between the sodium hydrogen carbonate and the carboxylic acid to make the carboxylate salt. And that makes it soluble in water, which makes it faster to absorb into the bloodstream, and therefore it's much faster to act. How interesting. All right, of course, carboxylic acids are involved in esterification. You make esters from alcohols and carboxylic acids. And for more details of how this occurs, I'm going to refer you to the video that I made on esterification. So if you want more details of how this reaction occurs, then head over to that video. But quite simply, carboxylic acid reacts with an alcohol. It's an equilibrium reaction, needs a strong acid catalyst, which means we write a little H plus over the arrow, and we make our ester. Now, as far as occurrence and uses, I found this table that has the natural source of the first 10 carboxylic acids. And there seems to be a fair few from goats. So the goats are still with us. But what I really want you to note here is that acids have an IUPAC name, but they're also given common names. And although we love the IUPAC rules and we always follow the IUPAC rules, this is not the case in everyday life. Most of the time, people will actually refer to these acids by their common names. So it's going to be really handy for you to actually be familiar with the common names of these carboxylic acids. Carboxylic acids, I mentioned at the start that your body is making carboxylic acids right now because carboxylic acids and carboxylate salts occur naturally as part of your cell metabolism. So the Krebs cycle, which is also called the citric acid cycle or the tricarboxylic acid cycle, this is one of the most important reaction sequences in biochemistry. And that's because it's responsible for making energy. It's responsible for most of the energy needs of any organism. And it also produces molecules that are building blocks for your body to be able, your cells to be able to synthesize fatty acids to make fat, steroids, cholesterol, amino acids for building proteins, and also the purines and pyrimidines that are used to make DNA. Now, it's called the tricarboxylic acid cycle, not because there are 3 carboxylic acids in it. There are many more than that. But if we look at citric acid here, you'll see that citric acid contains 3 carboxylic acid groups. And that's why it's called the tricarboxylic acid cycle. So look out for that. You biologists, I know, are all over this already. You know all about your Krebs cycle, but an interesting application nonetheless of carboxylic acids. Carboxylic acids are very important in making polymers. Just as an example here, we're looking at making polyesters. This terephthalic acid makes the polyester mylar. Now, mylar makes a thin film that is used for those squeezy yogurt containers, for people who haven't learned how to use a spoon yet. And for foil balloons, it's also used to make those thermal blankets you see in first aid kits, the thermal blankets that are used if somebody's suffering from hypothermia and you need to warm them up and you wrap them in that reflective blanket. That's also mylar. Okay, they're also used to make, this terephthalic acid is also used to make a polyamide polymer called Kevlar. Now, some of you may have Kevlar belted tires. Kevlar is a very tough polymer. So it's put into, you line your bike tires with Kevlar, with a Kevlar belt to try and avoid punctures. Also, bulletproof vests. These are made of very tightly woven Kevlar fibers. Again, very strong, very tough, even able to withstand a speeding bullet. Here we have the production not only of the polyester. polymers, but we have the production of polyamides here. Nylon 66 is one of the most important polymers, one of the very first polymers that was made, and it uses hexandioic acid, which is also called adipic acid, as one of its monomers. And of course, nylon is used to make threads, ropes, stockings, fishing lines, the strings of your tennis racket. So carboxylic acids, we really couldn't live without them. In the food industry, carboxylic acids are used as natural flavorings in fruits, also in vinegar. So we have ethanoic acid or acetic acid in vinegar. We have malic acid in grapes and apples. Citric acid, of course, you'd be familiar with the fact that that's in oranges and lemons and all citrus fruits. So they're very important natural flavorings. They're also used as preservatives. Lactic acid is a preservative, added as a preservative in food. Ascorbic acid, vitamin C, is an antioxidant. And tartaric acid, an emulsifier. Emulsifiers just prevent the separation of oil and water mixes in your food. Nobody wants their food to separate into the oil and water layer. That is just not nice. Carboxylic acids have important medical applications. They're present in pain relief and anti-inflammatory medications. So aspirin, probably less used today as a pain relief and more as a blood thinner, but there's the carboxylic acid group. Ibuprofen, you see this on the shelves, branded as Nurofen. And of course, this has a carboxylic acid group. Then we have naproxen, which is another anti-inflammatory drug. We see the carboxylic acid group. So they are all over the medical industry as well. If that's not enough, the cosmetics industry makes use of these as well. There is skin treatment, the alpha hydroxy acids. Where would we be without the alpha hydroxy acids? They unblock and clean your pores, they improve your skin texture, and they're used in whitening and anti-wrinkle treatment and acne treatment. And you can see the carboxylic acid groups. Yeah, these are alpha hydroxy acids, and that just means that there is a hydroxyl group on the carbon next to the carboxylic acid. So here we can see we've got a carboxylic acid group here, and on the next carbon, there's a hydroxyl group. And you'll see that that is the case. Here's the carboxylic acid in malic acid, and we have a hydroxyl group next door. So that is what an alpha hydroxy acid is. They're very, very important in those skin treatments. These products make billions of dollars every year. Everybody wants a bit of anti-wrinkle treating and a bit of improved skin texture. In anti-aging treatments, we have the aldobionic acids. They sound incredible. So they provide antioxidant and anti-aging protection, and they improve moisture retention in the skin. So ascorbic acid, retinoic acid, which is made from vitamin A. And we have azelaic acid or non-dioic acid. So these are all used in anti-aging treatments. Of course, because they're used in making esters, they're very important for artificial flavors and artificial fragrances. So we have a lot of different esters here that make fruity smells. We have citrus smells, sweet smells, and of course that's all put to use in the food industry as artificial flavoring and fragrancing. So next time you have your bubble gum, you will be eating esters that are made from carboxylic acids. When you spray your air freshener, you're going to be spraying esters made from carboxylic acids. If you head on to Macca's and have a strawberry shake, then you are going to be taking in a bit of ethyl butanoate, because that is the compound that's responsible for the strawberry flavor. That McDonald's shake has not been near a strawberry. It is all artificial. Of course, the sweet smells are made use of in the perfume industry. So finally, I want to talk to you about the fact that every time you work out, even when you're just sitting around doing nothing, I'd rather be working out, wouldn't you? Your body is producing carboxylic acids. Your sweat glands produce carboxylic acids, even butanoic acid. So the stench of body odor and foot odor is all about carboxylic acids. Now, dogs are able to track humans by detecting a characteristic blend of carboxylic acids in their sweat. So a tracker dog, they'll actually let the dog sniff a piece of clothing that the person they're tracking has worn, and the dog will maybe be able to recognize that particular blend of carboxylic acids. And of course, tracker dogs are trained then to follow the trail of that scent. But your dog recognizes you by your own personal blend of carboxylic acids. And that is why when you meet your dog likes to shove its nose into all of the places where you sweat a lot. So when your dog picks up that particular blend of carboxylic acids that it knows belongs to you, then it recognizes you. So the dog has to sniff out the carboxylic acids, which smell disgusting. It truly is a dog's life. Enjoyed learning a little more about this fascinating group of compounds, the carboxylic acids. If you found this video useful, or you just enjoyed some of those interesting applications of carboxylic acids, please consider giving the video a like. And as always, please subscribe to my channel so that you can learn more about this fabulous subject of chemistry. I am going to see you guys in the next video.